Let's start with normal distribution. Now, normal distribution is one of the most widely used distribution in universe. Now, almost every natural thing follows a normal distribution. Now, let's take an example of height of students. Now, let's say if I take total number of students and find their average height, let's say it will be around 5.5 feet, and most of the students are going to be around that 5.5, and the extreme values, that is, let's say more than 6.5 or less than 4.5, the probability or the number of students that will have those particular heights will be very less. So basically we get a normal distribution that looks something like this. Now, normal distribution is actually symmetric around mu or its mean. A normal distribution has parameters mu and sigma square, where the probability density function fx will be 1 by sigma under root 2 pi e raised to minus half x minus mu upon sigma whole square. Now this becomes our fx, where x is between minus infinity and infinity. So basically our values that our variable can take is minus infinity to infinity. Now the expected value of a normal distribution is mu, and variance of the normal distribution is sigma square. Now this is the only distribution that has its expected value and variance as its parameters. Now, just because this is not easy to integrate, we are not going to find expected value or variance for normal distribution. Usually they do not ask to find expected value and variance of normal distribution. And similarly, it is very difficult to find capital Fx. Our capital Fx, that is nothing but probability x less than a particular value x. Now, when we need to find this particular value, that is probabilities, what are we going to do? Now, for normal distribution, we have tables. Now, unfortunately, when we make tables, the problem is when we have two different parameters and x that is varying, the table is going to be very extensive, or it might be impossible to form. So therefore, we convert this normal distribution into standard normal before we can make, or before we need to find probabilities. Now let's study standard normal. Now for standard normal distribution, we say, now we have actually taken z as our variable because it is something that has been standardized. So basically we usually use z for our standard normal distribution. So we say z follows normal 0, 1. So any normal distribution whose mean is 0 and whose variance is 1 becomes our standard normal distribution. Now, how do we convert any normal distribution into a standard normal distribution? So if we have x follows normal with mu, sigma square, then we say our z will be equal to x minus mu upon sigma. This will follow standard normal distribution. Now, the probabilities for standard normal distribution are given in our table book. Page number 160 and page number 161, you will find probabilities of standard normal distribution. Now, always when we are looking at the tables, always look for the graph. The graph shows us that they have given us probability less than equal to z from minus infinity. So basically they are giving us this capital Fx, but for a standard normal distribution. Now, if you see, the value starts from 0, x is equals to 0, and values only go till x is equals to 4.4. Now, why do we have values only from 0 to 4.4 when values of our variable can go from minus infinity to infinity? Now, basically, if you see, probability for 4.4 it is 0.999999, or you can say it is almost equal to 1. So we don't need any value greater than that particular value. But what about negative values from, let's say, 0 to minus 4.4? Now for that, what we do is we use the property that is the normal graph is symmetric around its mean. So basically, for standard normal distribution, our mean is going to be 0. So this particular part of the graph is symmetric with this particular part of the graph. So if I need to find a particular probability, I can just use the property of symmetricity to find the other side of the probabilities. Now for that, we have a small, you can say, way to find those probabilities. Now if I say my z, if I need to find probability that my z, that means a standard normal distribution, is less than a particular value zk. For that, I'll say my zk first, let's say it is greater than 0. So if I need to find probability z less than zk, that will be equal to, I'll write phi zk. Now phi zk, again this is a standard way of writing that probability standard normal variable is less than this particular value. We can write it as phi of zk. Now in your table book you can find they have given us phi x, because they have taken x as their variable. So for that, we can directly use the probability that is given in this particular page. Now what if we need to find probability z greater than this particular value zk, that is greater than 0 or a positive value? So it will be just 1 minus phi of zk. Then what if zk is less than 0, a negative value? Then probability z less than zk. Now let's say this is that particular value zk. Now if this is zk, there will be a positive value on the other side, let's say mod zk. Now probability of positive values are given. So if I need to find probability z less than zk, where zk is a negative value, I am basically trying to find this particular probability. Now this particular region is exactly same as this particular region. That is nothing but probability greater than the positive value of the zk. So this will be same as probability z greater than zk if zk was positive. So I can say this is nothing but 1 minus phi of mod zk. And similarly, finding probability z greater than zk. So for this, I'll draw another graph here. So again, if I have zk here and mod zk, a positive value of zk here, then I need to find basically probability that is from zk to plus infinity. Now zk to plus infinity is same as minus infinity to z mod zk, just because the graph is symmetric. So I can say this is nothing but same as this, that will be phi of mod zk. So basically you can use these relations, find probabilities when we are doing sums. Now let's do a particular sum. Let's take an example that x follows a normal distribution with mean as 25 and variance as 36. Now let's find probability x less than 22. Now for this, or let's say x less than 20. Now for this, first of all, how would we write it? First of all, we'll show that our x follows normal 25, 36. Then we'll convert this normal distribution into standard normal distribution. We'll say z is equals to x minus mu upon sigma will follow normal 0, 1, and then our probability x less than 20. Now we'll have to convert this x into our z to find the probability. So what we'll do is, first of all, we'll subtract mu from both sides. So x minus mu, and that will be nothing but 20 minus, we'll have 25. Mu is nothing but 25, and then we'll divide by sigma. X minus mu upon sigma less than, we'll have minus 5 upon, then sigma is 6. So we get this, or we can say this is nothing but probability z less than minus 0.8666. Now basically in our table book you will find that they have just given us 0.86 and 87. They have not given us any more than that value. So let's take that we have 0.867, because they have given us only 2 decimal point digits. So we can take 3 decimal and then find the value. So first of all, this is nothing but zk is negative. If we have a negative value and we need to find probability z less than the negative zk, so basically we'll need 1 minus phi of mod zk. So I can say this is nothing but 1 minus phi of 0.867. Now let's find this particular probability from our table book. Now in our table book, you'll find probability for 0.86 and probability for 0.87. So probability for 0.86 is nothing but 0.80511. Probability for 0.87 is 0.80785. Now how do we find probability for 0.867? Now I would suggest, if it was let's say 0.869, I would suggest just convert it into 0.87, or if you have 0.861, convert it into 86. If you have other than that, all the values between 1 to 9, we are going to use interpolation to find the values. Now for that, we have 0.86 and 0.87 probabilities. We are going to use these probabilities to find our value of 0.867 using interpolation. So the formula for interpolation is nothing but y2 x minus x1 plus y1 x2 minus x upon x2 minus x1. So basically here 0.86 becomes our x1, 0.87 becomes our x2, and x is nothing but 0.867, and y1 is going to be 0.80511, y2 is going to be 0.80785, and use this formula to find the probability for 0.867. So you should get your probability as 0.807028. Now 1 minus, our actual value is 1 minus of that probability. So 1 minus will give us 0.192972. Now let's take another example. For the same sum, we need to find probability mod of x minus 25 less than 4. Now for this, first we'll solve the mod. So this is just positive value. So when we open the mod, we get probability minus 4 less than less than x minus 25 less than 4. Basically this says the difference between x and 25 is less than 4. That means it can be a positive difference or it can be a negative difference. That means our value can be between minus 4 to plus 4. So basically here we have this particular value. Now just because our mu is already 25, I am not going to solve this further because we need to make it into a standard normal, that is x minus mu upon sigma. Other than that, if I had some value, let's say 20, I would have added 20 to the whole value and then converted into standard normal. So here I can say this is nothing but probability minus 4 by 6 less than x minus mu upon sigma less than 4 by 6. This is nothing but probability minus of, this will be 6, 6 and 7 less than z less than minus 0.667. Again, I am taking only 3 decimal points just because in book they have given us 2 decimal points, and more than that we are just doing an approximation. When we do interpolation, we are actually assuming that there is a straight line between those two probabilities. Now actual value might be slightly different, but interpolation gives us nearly accurate value. So already we are doing a sort of an approximation. So here if we just take 0.667 instead of 0.666666, it will still be accurate enough. Now let's assume if we need to find probability z1 less than z less than z2. We have 2 different values and we need to find probability that is between those values. So if I take this particular graph, we need to find probability between these 2 values. Let's assume this is z1 and this is z2. Now z1 and z2 can be on one side of the 0 or it can be on the other side of the 0, or it can be different values, does not matter. Okay. So if I have z1 and z2, I need to find probabilities between these 2 values. So I can say this is nothing but probability from minus infinity to z2 minus probability from minus infinity to z1. So that is nothing but probability z less than z2 minus probability z less than z1. Now I'll explain it again. We need to find probability between these 2 points z1 and z2. So that can be nothing but probability minus infinity to z2, this particular value, minus this particular value, that will be minus infinity to z1. So that is probability z less than z2 minus probability z less than z1. So for this particular one, I can say this is nothing but probability z less than, this should be positive value, sorry, 0.667 minus probability z less than minus 0.667. Now this negative value, again using this I can say is nothing but probability z less than 0.667 minus of 1 minus probability z less than 0.667. So I can say this is nothing but 1 minus, or sorry, 2 times phi of 0.667 minus 1. Then find the phi of 0.667 using interpolation. So in our formula table book, find 0.66 and 0.67. So we'll have x is equals to 0.66 and 0.67, see their probabilities, and use the interpolation to find probability for 0.667. So we are getting our probability using interpolation as 0.74761 and final answer is going to be 0.49522. Now the last distribution that we are going to study is log normal distribution. Log normal distribution was derived, is not a naturally founding distribution. So it was derived so that we can find a relation between some variables that are nothing but some powers of particular value. So if I need to find relation between y and x, so I'll take log on both sides, and this will be log to the base e, or I can say ln y will be equal to x. So if my x is following a normal distribution, then my y will be following a log normal distribution. Now simply, if I have a variable x following log normal distribution with parameters mu, sigma square. Now, though log normal distribution has the same parameters of normal distribution, they are not the mean and the variance of log normal distribution. So, if we have a variable x following log normal distribution, then we say log of x will follow normal distribution with mu, sigma square. So, it is basically the mean and the variance of this particular normal distribution. Now, this log is also to the base e. Every log that we are going to study in this particular course is always going to be log to the base e. So, in your calculators, you have to use ln, not log, because in calculators, log is nothing but log to the base 10 and ln means log to the base e. So, basically, log x follows normal distribution mu, sigma square, where its fx is nothing but 1 by x sigma root 2 pi e raised to minus half log of x, or ln x, minus mu upon sigma whole square. So fx looks very similar to normal distribution, but it's not. And here we have x greater than 0. So the values that x can take is only from 0 to infinity, as values inside log has to be always positive. So therefore, the values that are variable in log normal distribution can take is going to be 0 to infinity. The expected value of a log normal distribution is nothing but e raised to mu plus half sigma square, and variance of our expected value, variance of a log normal distribution is e raised to 2 mu plus sigma square into e raised to sigma square minus 1. So this becomes our expected value and variance. Again, you don't have to learn these values. These are given in your table formula book on page number 14. Now, if we need to solve or find probabilities for log normal distribution, first we convert our log normal distribution into normal distribution, and then we convert our normal distribution into standard normal distribution. So, if I need to find probabilities for a variable x that is following log normal distribution with mu, sigma square, then first we'll convert it into log of x is following normal with mu, sigma square, and then we'll say z, which is equals to log of x minus mu upon sigma, will follow standard normal, that is 0, 1. So this is how we'll convert our log normal into first normal, and then from normal to standard normal, and then we'll find probabilities for standard normal distribution. Now let's take an example. If I have x follows log normal distribution with 5,6 and we need to find probability x less than 3000. Now for this, first of all, we'll write x follows log normal 5,6. Then we'll convert. We'll say log x will follow normal 5,6. Then we'll say our z, that is equals to log of x minus mu upon sigma will follow standard normal 0,1. Then we'll have probability x less than 3000. Now we'll have to convert this into standard normal. First take log, subtract by mu and then divide by sigma, or I can directly write it as probability ln x minus mu upon sigma less than ln of 3000 minus 5 upon root 6. Use a calculator to find that particular value. Always remember, when you are using values inside log, when you put ln or when you put log, it is going to show a bracket. Then I put 3000 and then I have to close the bracket, or else it will take 3000 minus 5 inside the log. So we get probability z less than 1.2273. Now again, I need only 2 decimal points. I'll take 3 for a better approximation. Fourth is not needed. So I need to find probability z less than 227. Again, we'll have probabilities of 1.22 from our table. We'll have probabilities of 1.23 from our table, and then we'll do interpolation. So the probabilities 1.22 is 0.88877 and 1.23 we have 0.89065. So use your interpolation to find probability for 1.227. Again, this is our x1, this is our x2, this is our x, this is our y1, this is our y2. We get our probability as 0.890086. So this is 0.890086. Now statistics is very widely used to prove different theories. What we do is we do some experiments, then we collect data, then we analyze them, and after analyzing we try to prove that whatever our hypothesis was is whether proved using that data or whether it is not proved using data. Now whenever, let's say I am being a scientist, want to prove that my hypothesis is correct in front of a few people that are going to judge whether my experiment was done correctly or not. So for that, what we need is we need some kind of data points that we can put in our particular, let's say, formula to get some kind of output. Now any hypothesis will give you some kind of formula that will have some kind of input, and that should give us a predictable output. Now let's say our formula is some kind of distribution that we have already studied, or maybe some distribution that we have not studied. Now I should be able to put some values and to be able to predict the output of those values. Now if I take some values that I have already known, the people that are judging me would say that I have some kind of bias towards those values. So therefore we try to select random values. Now there's a book of random numbers that gives us value between 0 to 1. There are many values, or there's a very wide book, and that gives us value at a very large number of decimal points. Now unfortunately those values are just between 0 and 1. Now our distributions have different range of our particular values. Let's say if we talk about an exponential distribution takes values between 0 to infinity. Normal distribution takes minus infinity to plus infinity. Then similarly, if I have a discrete distribution will take discrete values. Again, we cannot find discrete values using those random numbers between 0 to 1. So therefore, what we do is we simulate those numbers into the range that we need our values to be. So basically, that is our next topic, simulation. So we take some random numbers from those random books. Here in our question, they'll give you those random numbers, and then we simulate it into those values that are between our particular range. So they are going to give you values, let's say u, that are going to be between 0 and 1. And because those values are going to be selected randomly, we can say that they are following a uniform distribution between 0 and 1. We can select the probability of selecting any value would be uniform. So therefore, we'll say our values that are going to be selected u will follow uniform distribution 0 and 1. Now let's say we need to simulate our value into some variable x of which we know the capital Fx. Now capital Fx might be anything. So what we are going to do is we are going to relate our capital Fx with those particular value u. Now our small fx being probability density function for continuous distributions or being probability distribution functions for our discrete distributions will not be related to u. Why can we not relate it to u? Because those values have different ranges. Now whenever we take capital Fx, that is cumulative probability. Cumulative probability will always have value between 0 to 1. Therefore we equate our capital Fx with u, because capital Fx will always have a value between 0 and 1, as well as this u will also have a value always between 0 and 1. That is why we are always going to equate capital Fx with our particular value u. So what we do is, now we use the inverse function. So we can find easily x is nothing but f inverse of u. And we put different values of u and find different values of x that will be used in our particular hypothesis. Now of course we are not going to use any kind of hypothesis. This is a small question of let's say 2 marks or so, in which we'll have the uniform values given to us, and we would need to find x values or simulate x values to get or our answers will be the values of x. Now let's take a question. Now in this question they have said, consider the random variable x having a distribution with probability density function as this, where nu is greater than 0 and lambda are the parameters of the distribution. First, show that the cumulative distribution function of x is given by this particular value. So first of all, our fx is nu lambda x raised to nu minus 1 e raised to minus lambda x nu, where the values of x are going to be between 0 and infinity. Now we need to find capital Fx. I'll just write capital F1, and that will be integration from 0 to this particular value x1 fx dx. Now whenever we have such values where we have a function of x and also another function of x, these are two different functions. One is an algebraic function and the other is exponential function. Now, we usually use integration by parts, but here if you see, we can actually use substitution method. if I substitute my minus, or actually lambda x raised to nu as some other variable, so I am substituting lambda x raised to nu as my t, then my dt will be equal to lambda nu x raised to nu minus 1 dx. So this particular x raised to nu minus 1 dx will be substituted as dt. So this becomes integration 0 to, now whenever you are substituting those values, you will have to substitute, instead of x1, when I put x1 here, my t becomes lambda x1 nu. So you will have to also substitute the limit, and 0, I get t equal to 0, and then I get e raised to minus t, because this new lambda x raised to nu minus 1 dx becomes my dt. This will be e raised to minus t upon minus 1, 0 to lambda x1 nu. So this becomes 1 minus lambda x1 raised to nu, where my fx is nothing but 1 minus lambda x raised to nu. So this becomes our capital Fx. Now let's see the second part of our question. Now the second part reads, determine by simulation a value of random variable x where nu is equal to this and lambda is equal to this. Now you are given a value of u. Now they have given us u is equals to 0.671 from a uniform distribution 0, 1. Now we have to determine, first of all, they have given us nu as 1.1 and lambda as 0.2. So our capital Fx can be related to u. Now usually they might ask us to find multiple values of x with multiple values of u. So usually what we do is we make a general formula and then we put our value of u. So I can say this is nothing but 1 minus lambda x raised to nu is equals to u. So we get lambda x raised to nu as 1 minus u, and x will be nothing but 1 minus u by lambda raised to 1 by nu. Now we can put the value of nu as well as value of lambda, and you can also put the value of u. So 1 minus 0.671 upon 0.2 raised to 1 by 1.1. So using our calculator we get value of x as 1.572224. So this is the value of our simulated value of x where u is equals to this. This is the method you are going to use when we are going to use our continuous distribution. For discrete distribution there is a different method. For that we are going to see another sum. The question reads, let x be a discrete random variables with the following probability distribution. First, simulate 3 observations of x using the following 3 random numbers of a uniform distribution on 0, 1. Now, first of all, they have given us x as 0, 1, 2, 3. We have probability x is equals to x as 0.4, 0.3, 0.2, 0.1. We'll always equate our capital Fx or cumulative probability to find our simulation. So for that we'll need to find probability x less than equal to x, that is nothing but our capital Fx or cumulative probability. Now For cumulative probability, we'll have 0.4, 0.7, addition of these two, it will be probability x less than equal to 1. Then now probability x less than equal to 2 will be 0.4 plus 0.3 plus 0.2, that becomes 0.9, and this becomes 1. So all the values that will have probability between 0.4 to 0.7 will have the value 1. All the values that has probability between 0.7 to 0.9 will have value 2, and all the values that has values between or probability between 0.9 to 0.9 to 1 will have value 3, and all the values between 0 to 0.4 will be related to 0. Now simply what we can do is we can use our values. U1 is given as 0.4936. This is our first uniform value we have to simulate, and our x1. Now see, this particular value is between 0.4 to 0.7. So any value that is between 0.4 to 0.7 will be directed towards 1. So our x1 will be 1. Then U2, the value is 0.7269. Our x2, now again this value is between 0.7 to 0.9. The value corresponds to 2. So x2 becomes 2, and U3 is 0.1652. So our x3 should be equal to 0. So this is how we'll simulate our discrete distributions.